Okay, well, welcome back everyone for the last talk in our session today. It's my pleasure to introduce our last speaker, Professor Amir Farbin. Amir is a faculty member in the Department of Physics at UT Arlington, and he is a member of both the ATLAS experiment and sort of also the DUNE collaboration. So Amir is a particle physicist. He's one of my colleagues on ATLAS. And among his interests in searching for new physics and other elements of these experiments, he's particularly interested in deep learning, which is one of the common threads, as he'll tell you, between these experimental efforts. So without further ado,
thanks,
Amir.
Thanks, Chris. Let me turn this on. Well, thank you for inviting me. This has been a lot of fun. I was an undergrad at MIT, and I haven't been to Boston in a long time, so it's been great being to walk around my old city. So anyway, so I'll tell you, I may have bitten off a little bit too much in trying to describe to you sort of all the activity that's going on in high energy physics and deep learning, but I thought it was kind of a useful thing to sort of see how broad there it is and try to present a lot of problems that are out there that may be actually interesting to people in this room who may actually have some ideas and don't have a data set to play with, or we can provide a data set or those type of things. So I thought, and also I've given a lot of these kind of talks actually to different machine learning and deep learning and data science groups, and at times and also physicists. So to the physicists, I'm teaching them, trying to explain sort of deep learning techniques to the deep learning and machine learning people. So I'm trying to teach them a little bit of physics. So all that stuff is kind of here all together, and based on your reaction, I will try to focus and defocus as I see fit. So my overview is that, so I'm going to really not talk too much about physics, very minimal physics. I'll tell you about the experiments, why we do them and how we do them. I'll tell you about the data, how much data we have and what the data is and what we do with them. And then I'll tell you about the problems and challenges that we face with these things. And then I'll tell you how deep learning is applied to address some of these problems. And the first applications of deep learning in our field happened in 2014. But most of the activity that I'm going to tell you about is really from less than a year ago. All this stuff is very, very new. They're mostly first attempts and demonstrations. There are no physics measurements actually that have been done in my field that actually have employed deep learning techniques. And there's also a lot of potential applications, and I'll mention them just so you know there's interesting problems that people are hoping to tackle, but we haven't really gotten there. And a lot of this is about preparing the data sets, and we're mostly in that phase. And then if there's some time, actually, I got here Friday, but we were able to do something semi-interesting, so I'll tell you about what Chris and Paul Jackson and I worked on this Friday a little bit. Now, two things that I want to sort of point out in terms of benefits of deep learning is that if we actually apply it to our data, we can get better, faster, easier made sort of algorithms to do stuff. But deep learning also has indirect applications where it's an analysis tool. So I can use it to be able to figure out how to do something more conventional better. So this is one of the points that I'll try to make. Now, if you find something interesting, I want to invite you to talk to me, and I can put you in touch with people who are working on those problems. And what I'll do is I'll introduce some soon-to-be public data sets that you could use. These are big data sets that we're designing specifically to be able to collaborate with people in the field. Now, there's a lot more on the slides that I want to discuss. It's probably too much, but what I'm hoping is that if there's something you're interested in, then you'll read that slide more carefully and think about it, and so it's kind of just for reference. All right, so let me talk about the experiments. Oh, I didn't realize it's going to do that. All right, how nice. Okay, so HEP experiments, just from a very basic level, there's really two parts of them. First, you need a source of the particles, and typically, for example, you have a collider, like the LHC. You collide particles together, so you get two protons, for example, you collide together. And the point is that you're going to try to make some new particle, or some heavy particle that doesn't exist very, naturally in our environment. So you make, for example, a top. And it's not, you don't see this top. What you see is this top will very quickly decay to other particles, like a B quark and a W. And then those will also further decay. And eventually you get to some final particles that live long enough to actually go through your detector and interact with it so you can tell that something happened. And then you work backwards to infer what was there. So then to be able to see this stuff, you have to take a picture of it. You actually have a detector. And that's what the second component is. You have effectively a big camera. And what it does is that it just takes, it detects all those long-lived particles that go through. That's basically what we're doing. And there's various types of detectors, but there are sort of standard things that happens. We do particle tracking, calorimetry, we have muon system, we do particle identification, and I'll explain a little bit some of these things to you, okay? Now, in terms of actual experiments, this is really, all the physics in this talk of any interest is really just in this one slide. I kind of squeeze it all in here. There's really three, I would say, big thrusts now within sort of the collider particle physics sort of community in terms of directions that we're going. The primary one is the energy frontier, which is, is happening at the Large Hadron Collider, which is at 13 TeV now. And this machine would be upgraded and by 2025 will run with much higher luminosity, much more protons in interaction, so we get more data. That's what that means. And then maybe in the decade after that, maybe we'll have maybe a 33 TeV LHC, or maybe the Chinese will build a 100 TeV machine for us. So this is the energy frontier. And really what this is aimed at is that, as you're probably aware, in 2012, we discovered the Higgs. Now we're moving on to actually studying the properties of this Higgs and the new other types of Higgses that could actually exist. We're testing something called naturalness, and you know, if you want to sort of tell your friend what that is that doesn't know any science, you say, well, it's kind of testing to understand, was the universe an accident, or was there a mechanism for things ending up? And basically what's going on is that in order to keep the Higgs really, really light, we need to find some natural way, either we need to fine tune our models, 1 part in 10 to the 18, or we have to find some natural way to do that. A natural way would be something like extra dimensions or supersymmetry, and we're looking for those signatures of those things. That's the primary motivator for the work I think that Chris and I and a lot of the people do here. And the other thing is that you can find dark matter, and we have good reasons to believe that dark matter may be at the same scale of this that addresses this natural press problem. Now, there's another class of experiments that are happening that work at the intensity frontier. Here now you're trying to get a whole lot of particles of a particular type to understand the properties of particles really, really well. These are, so I did my PhD on the Babar, which is a B factor experiment. They make these mesons that have B quarks in them, and we start to measure the properties of those particles really, really to depth to understand, to see if we can find indications of new physics there. There's also neutrino beam experiments. Now, neutrinos are very elusive particles, and we have just found out, you know, in the late 90s that they have mass, and we don't know much of their properties. So now we're trying to make really intense beams of neutrinos. They're very elusive. They don't interact very much, so we need a whole lot of them and a very big detector to actually see them interact to be able to start measuring their properties, and we're trying to understand those. So that's basically what's going there. And there's a whole sort of a big program that's going on. There's right now some experiments like NOVA and microblue that are running. Soon there will be these short baseline experiments. But really everything is converging on this program that's going to be the flagship HEP program in the United States, which is going to be, shoot a beam of neutrinos from Fermilab, 1,300 kilometers to a mine in South Dakota where we'll have a big detector, and we're going to do measurements there. And so this is really the big physics that's happening here in this country. And the idea is basically we're going to study the properties of after we do these experiments, B quarks or neutrinos. And you can do auxiliary physics. Since this thing is, supernova give most of their energy actually in neutrinos. So this actually, you can study supernova through neutrinos, which is really cool. You can look for, there's actually ways of getting dark matter, and you can also look for proton decay. So you can do auxiliary physics at the same time. Finally, there is another type of collider experiments that we could do that we're hoping will get built in Japan in the next decade or so. And these are sort of I would call the precision frontier, but normally they're actually at the energy frontier. And basically what we're going to do is build a machine that's very clean and allows us to really measure the properties of Higgs or any other thing that we hopefully will find eventually at the LHC very, very well. So that's basically, that's the physics motivations for all this kind of stuff, and that's what's going on in the next decade or so. There's other things that are of interest, but these are the primary ones, okay? So then, how do we actually see these particles? And I'm not gonna go through this too much, but, well, there's really two basic things that we do. We can, for charged particles, we know that when a charged particle goes through matter, it ionizes matter. And if you can actually detect a charge, we can figure out the trajectory of that. Now, the ionization is a stochastic process. As it's going through the matter, it will interact and leave some amount of the energy, and that amount of energy is stochastically determined, right? And then if you put that particle, if it's a charged particle in a magnetic field, it'll curve, and that curvature will give you, if you can measure that curvature, it will give you measurement of momentum. Okay? So that's what a tracking detector does. You can also measure the energy loss. The energy loss will tell you in principle something about actually the type of particle it is also. So we have tracking detectors this is the principle that work on. So for example, I guess this is it. For example, this is a event in Atlas. You can see all the different tracks. So these are tracking planes. These are silicon that when a particle went through, a pixel lit up, and then we do pattern recognition and draw lines through these things, and we find the trajectories of those particles. And then what's interesting is, at the LHC, for example, when two bunches of protons pass, these pass at 40 megahertz, 40 million times a second they pass, but every time they pass, we have something of order now 30 to 50 individual protons that collide, and you can see them. That's one collision, that's another collision, and so on, okay? And the task of doing this is really, here is, for example, this detector sort of unrolled, and you can see, okay, I see sort of a pattern of hits, and I have to associate a pattern of hits together and fit a track through them. That's the task there, okay? So that's tracking. Another way that we see particles is if you put enough stuff in front of a particle, almost every particle will eventually shower. It will eventually convert to something else and deposit all this energy into the material. And then we can measure that energy by observing the secondary particles that come out. Okay? And there are two types. I don't want to go too much into it, but there's sort of, so the lighter particles we can probe, they interact electromagnetically. The heavier particles will interact with the nucleus. And we basically, by looking at sort of the deposits in here, we can figure out what type of particle it is and what the energy of the particles are. Okay? So here, calorimetry, here's, for example, the Atlas calorimeter. It's, there are different technologies. For example, with CMS, they use crystals, and Atlas, we use liquid argon. The Atlas calorimeter has about 200,000 cells. If you think about what actually comes out of it, it's sort of a 3D image. This is at a lower resolution than all the full granularity. And if you look at it, if I take the calorimeter, which is composed of multiple layers, and I just look at the layers, stack them on top of each other, you can see the granularity changes as it goes through. And this is sort of one sort of set of particles that went through the detector and left some pattern of energy deposits in there. And so you can see it here, for example. You can unroll the detector and you can see in the calorimeter, I saw 3 particles were in the calorimeter and so on. Okay, so that's the other technique. So then when you put it all together, what we're doing is we're trying to measure the properties of the particles that live through long enough to go through the detector. And so there's different particles that can interact differently with different parts of the detector. And based on those sort of signatures, we figure out what the particles were and what the energies are. And that's our starting point to be able to start doing the physics, because then we're going to try to put those particles together and say, was there a top in this event? Was there an Higgs in this event? Okay, so that's what we do. Now, neutrino experiments work a little differently. As I said, neutrinos are very, very elusive, and what you look for is that when a neutrino comes in, it'll very rarely interact with a weak interaction with, let's say, the nuclear. And what will happen is that it'll interact, and if you have the right type of interaction, it'll give off a lepton, which will tell you what type of neutrino it was. If it's an electron that comes off, it's an electron neutrino. But most of the physics that we actually need to do there, we only have to be able to tag what kind of neutrino came in, and then what the energy of that was. And actually, most of the physics we can do by just those 2 measurements. That's sort of neutrino physics. Now, to do neutrino physics, there have been different detectors, but one that may be worth mentioning, Super Kamiokande, that in the late 90s discovered neutrino oscillations. And the way that worked was that when those leptons and secondary particles go, so the target was water, so it's a big vat of water on the ground, and a neutrino will come in and from the solar sources or other sources. It interacts. The secondary particle then will go through that water, and if the particle is going faster than the speed of light in that water, what happens is you get something called Cherenkov radiation, which is analogous to a sonic boom. Okay, and what that's a cone of light that comes off, and by seeing that cone when it gets projected on the sides of the detector, it looks like an image. And by measuring these things, you can tell what kind of particle it was, what the speed of the particle was, and those type of things. That's one technology to be able to detect. Now, what's happening for neutrinos, there's been lots of different technologies to be able to detect them. And I'm not going to go too much into it, but what we're going towards is a new technology called liquid argon time projection chambers, which we're going towards, and this is the technology chosen for the flagship experiment that I explained to you, DUNE, that the US is going to pursue, and all the experiments are happening now leading up to it. Because we expect to have about twice the detection efficiency. And these are really, really cool detectors in that you have a big vat of liquid argon. The neutrino interacts, the secondary particles will go through it, will ionize that liquid argon, and when you put this in an electric field, before those ions recombine, you drift all those ions off to the side, and then you collect them on wires that are situated in different orientations. And if you just look at the charge that you see on a wire versus time, you get a beautiful image of actually what happened inside the detector. Okay? And so that's how these experiments work. All right, so let me tell you a little bit about the data. So let's switch into the LHC again and think about how much data we get at LHC. So let's do a back level calculation. So our detectors have of order 100 million electronic channels in them, okay? And we have 40 million collisions a second. And if you do things smartly, all this stuff ends up being about 1.5 megabytes per event. So that's about 60 terabytes a second of data that's actually is in the detector. Ends up, by the technology, when we designed this detector, we could not physically read that much stuff, because if you wanted to do that, the whole detector had to be fibers coming out of it. So we can't actually read all that data. So all that data is stored on electronic buffers on the detector itself, and we have a system called the triggering system, which will look at a coarser subset of that information and try to very quickly make a decision is this event that I'm looking at interesting enough for me to actually read it off the detector. And then subsequently, we'll go through and look at that event further and further and further, and we'll take that data and take it from that 40 million collisions per second, that 40 megahertz, down to something of order of kilohertz, which is what we actually write out to disk and tape, okay? And we can do that because, fortunately, what happens is that, well, the things that are interesting to us, I don't know, it's fortunate, maybe it's unfortunate, is that it happens very rarely. The things that we're looking for are 1 in 10 to the 11 typically. So for example, here are standard model processes that we know about, and here are the sort of processes that we're interested in. This is sort of the cross-section, this is the rate, this is a simple conversion as a function of the mass of the sort of particles. So this is the stuff that are sort of our backgrounds, and these are our signals. And they're much, much rare. And so we look for the specific sort of signatures of these things and try to pull this out as we're live, as we're taking data. And in fact, our analyses are exactly this also. What we do is we keep on whittling this data down and down, more and more and more and more, until we maybe end up with just a handful of events. And based on those handful of events existing or not existing, we make it a claim of discovery or a limit on the existence of a particular particle. Okay, so that's this is the easier idea. Now this data, if you put it all together, right now Atlas and CMS, each of those experiments record about 10 petabytes of data a month. Okay, and I think we may have actually be going above that because the LHC is doing very, very well recently. Okay, and the high luminosity LHC that we're going to have may have up to 100 times more data than this. All right, so then what do we do with that data? Well, the data comes out of this thing and comes out of our sort of what I call the high-level trigger at about 1 kilohertz. And what we do is these are electronic signals. So of this particular detector element lit up, we run something called reconstruction to be able to look at those signals, look for patterns, and try to identify those particles. Okay, so that's what so we do that. Now once I've got that, I'll go and put that through what I will call a derivation. So I take that data, I've looked at all that events, and I look for the signature of the particular new physics model that I'm interested in, and try to whittle down the data to the subset that is enhanced potentially in that particular signature. So what we do is we do multiple steps of reduction of data into smaller and smaller sets, throwing out information, throwing away events, until we get to some small subset that then I can run some statistical analysis, statistical test, and test for the existence of something or not. That's for analysis. Now there's other data paths that we have. To be able to do all this stuff, and I'll explain this in detail, we also do simulation. And you can either do this simulation, what's what we call full simulation, which I'll explain to you a little bit, which is very computationally intensive, or sometimes you can do sort of fast simulations that get you away. But typically, if we do this right, this full simulation will pipe it through the exact same chain so that it is as close as we can get to what actually happens to the real data. Okay. All right, so let me tell you a little about how we actually do reconstruction. So you have to think about there's millions of channels, and each channel, what I've done is I've digitized some signal that's coming out of this. And the first thing I got to do is something called feature extraction. I have to say, hey, actually, this channel lit up. That's the first step. So for example, in a calorimeter, I'll do feature extraction, I'll look at the channels, and I'll say, aha, I'll turn the channels to what I'll call cells, because I might combine a couple of channels, and I'll go through those cells, and I'll say, okay, these actually cells sort of lit up. And then what I might do is then say, okay, well, one particle may have lit up multiple cells that are next to each other, so I'll do some clustering. So I'll say, so these are a cluster of cells. And then it may be that actually this particle came in a group of particles known as a jet, and I want to do further clustering of those jets, and I maybe do some calibrations in between, and I'll make a jet by clustering those again. So this is typically the type of thing we do. For tracking, it's similar. It's similar things, and we'll go through tracking in a little bit more detail. But it's an algorithmic steps are looking for particular patterns and combining things and doing the next step and so on until you get all the way up to particle candidates. So if I do all this stuff, I'll do pattern recognition, so I'll do tracking. So if I find a track, for example, in an electromagnetic cluster, I'll know, oh, that's an electron. So I'll say on my output, here's an electron with this energy and these properties. And it's up to the analyst to go pick up that event and look at that electron and say, is that really an electron? And then does that event and everything else consistent with whatever I'm going to be able to test, okay? And this, right, all right. I think that's what I have to say, okay. All right, and then how do we do the data analysis? Well, what are our objectives for analysis? Well, we can do, typically we do a lot of searches, so we're doing hypothesis testing. Does this particular SUSY model exist or not, okay? And this is really done through likelihood ratio tests like this. We'll do measurements. Sometimes there's the top quark there. We want to measure the mass, so we want to measure it. So we'll do something like a maximum likelihood estimate or maximum likelihood fit to do that. And usually we don't see anything, so we set limits. So we do calculate confidence intervals. All of these stuff, every one of these, of course, is based on a likelihood, which is considering that every single collision is independent of every other collision. This is just n independent events with identically distributed observables. So we can just take a product of the probability of seeing any particular event, keep a resemblance factor there, and this is the probability of seeing that particular data set that you had, okay, the likelihood. Now, the significant part of data analysis actually is approximating this likelihood. That's what we are sitting there and trying to do, right, effectively. Now, just to give you a sense, this is a slide from my friend Kyle Cranmer. Here is, we may go and for example, the Higgs, you can look for the Higgs in multiple different final states it can decay in, and then different experiments. So Atlas and CMS did that. But we want to get the best measurement. We want to then combine them all together. So for example, this is the actual Higgs combination, which each one of these is a different final state from a different experiment. We combine all these together, and this is sort of the structure of all the sort of the relationship between the likelihood. This is the computation of the likelihood. We'll take the likelihoods from every one of these measurements, we do it all consistently, add it all together, and then do a fit and be able to get a combined measure of the cross-section of the Higgs or something like that, okay? This is the type of thing we do. Now, how do we do the approximation of the likelihood? Well, physics is all about establishing very precise models. That's why we're doing physics. I want to understand things very, very fundamentally, right? And it's the oldest science. We've been doing it for hundreds of years, and we've done pretty well. So we have really good models of our data. So unlike many other fields, we actually understand our data extremely well. And so this allows us to actually do multi-step ab initio simulations. I can just, starting from scratch, be able to simulate something that looks very, very similar to what I expect to see out of my detector. And we'll do that in multiple steps. First of all, the basic physics is written in the standard model, and the new physics is written in the language of quantum field theory, and we have this Feynman diagram, perturbative mechanism to be able to compute things to a certain order and a certain precision. So we'll go through that and basically compute the probability of seeing a particular event and generate events through a Monte Carlo process to be able to do that. And what that actually tells me is that if I have two protons, for example, they come together, two of the quarks in each of those protons will interact, they'll come together, and then what's the probability of seeing a top quark with these sort of properties, with these four vectors of momenta of the decay products going this one direction, right? So that's sort of what I get out of here. And I use that to generate Monte Carlo. But what I have here is quarks and leptons coming out of this. But those quarks, we never see quarks alone. Quarks very quickly, they don't like to be alone. They'll go and they'll pick up other quarks from the vacuum and hadronize and turn into a shower of particles called a jet. Now that process, so what I call hadronization, is a soft QCD process. It happens at low energies. It ends up, perturbation theory, QCD is strong at low energies, so you can't do perturbation theory. So we do this by models, empirical models that we have fit to the data. Well, semi-empirical because there's some physics intuition that we put into them, but we've taken all the experiments from before, we've taken these models and tuned them to be able to get us something that looks like what we expect from a detector, because we can't actually do the computation of what actually is happening there. And then once we've got so I took that quark and I turned it into the spray of particles that came after that quark hadronized. Then what I have to do is take each one of those particles and propagate it through my detector and simulate the interaction of that particle with the detector, which is a stochastic process. And the way we do that is through basically doing a sort of detailed multicolor integration over the microphysics of how these particles interact. Okay? That's our simulation. We use something called J-on-4 for doing that. Okay? And then finally, once we've done that, and now I know this particles will go into this detector and lift energy in these different places, then I have some model that I've built based on calibrations and test beam of how the detector would respond to particular energy deposits. Then I'll actually then go through and even simulate the electronic response of that detector. And then once I've done that, now I've gotten something that looks very, very close to what I would have gotten if this particular thing actually happened in my detector. The output looks identical, and I can take that output and pipe it through the same reconstruction algorithms and run the same things as we did before. Okay? So this is how we do, we sort of try to approximate the likelihood by running our simulations in this way. Okay? So what's the problems here? So let me tell you about 3 problems that we have. Okay? So one, I'm switching again back to the neutrino experiments. One of the problems that we have, and this is something that I think I'm putting it first because I think this is the most tractable one, is that it ends up with the neutrino experiments that are, these detectors are very new, and we're not very good at these reconstruction algorithms. And in fact, Microboon, which is the current sort of running experiment of this type, they don't have a neutrino oscillation result because they can't actually do the reconstruction by hand. It ended up being very, very difficult. And even though we have all these sort of things, these tools and common tools shared across experiments to do this stuff, we're not doing a very good job. And in fact, the only experiment that saw neutrinos and did neutrino measurements with liquid argon experiment that did it with liquid argon, saw neutrinos, use hand scans. Ends up that your eye does better than our algorithms. And they use people looking at the data by eye to do the pattern recognition. That's how I ended up doing the physics, because we couldn't do it. Okay? So this is actually a problem. And if you think about it, these things look like images. Image identification classification problems, for example, or algorithms from deep learning are perfectly suited for this type of things. Okay? So that's one problem that we have now. It's a serious problem that's actually a big problem.
Usually you require labeled data, though, to do this sort of classification.
Look, so we can, first of all, we have very good simulations. And also we have test beam. Okay, we can also, okay. But good question. All right, so the second problem, now I'm switching back to LHC. And I'm not thinking about LHC today, I'm thinking about LHC 10 years from now when we have 100 times more data. It ends up, computing is probably the biggest challenge of the high-performance LHC. We'll have higher granularity detectors, so there'll be, every event will be larger. And then every time we have bunches of protons pass each other at 40 megahertz, instead of 50 collisions, we're going to have 200 collisions on top of each other, right? And that ends up, when we're doing the tracking and trying to do the pattern recognition of here's a track that went through, here's a hit here, 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 that combinatorics gets really bad and it's intractable. In fact, I don't think we have a single event that has actually been able to complete a 200 collision on top of each other tracking. We can't do it. And I'll show you slides later of the projections of where that would probably go. The data would be about 100 times better, so we have much more data, so disk is actually an issue. So these are some projections from the experiments of how much it's going to cost for us to be able to do these measurements. So if you do that, and these actually are assuming good things like Moore's law is still working, which in fact it isn't anymore, at least for the past few years and probably for the near foreseeable future. It's assuming that there's actually more scaling still. We are factors of 5 to 10 off from being able to do the computing in terms of cost. It will cost us 5 times more than we're spending today to do the computing for LHC, at least, if not maybe much, much more. So this is one of the biggest problems. Now there are potential solutions. First of all, we can apply more resources, and one of the things that are happening is that we are now starting to do work on the supercomputers. That's one thing that we're doing. That's just great. And those are being available to us. So that's a lot of extra computational power that we get for free potentially, so that helps. But we can also rely on these new highly parallel processors like GPUs and multi-core processors. And these things already run typically for some tasks 10 times, 100 times faster than CPUs. But actually it's been extremely difficult. It's been a huge struggle for us to take because our events, our data has been embarrassingly parallel, and our software is never designed to do these things in any other way. We've had an incredible difficult time being able to actually efficiently port our code and our techniques, and we have millions and millions of lines of code and spend hundreds of millions of dollars writing this code, be able to do this in a parallelized way. And we've actually haven't had very big successes here. So this has ended up being difficult. So this is the status. So this is just the other problem. All right, so then the last problem is that coming back to this likelihood approximation. So I just described to you how we do our simulation. So I need the probability, if I've got an event, I want to understand what is the likelihood of that event. The better I do this, the better I can do my measurements and everything I do. So the better I estimate it, the better it is. I ended up, though, in the set of steps that I described to you, step 2 and 3, the hadronization simulation can only be done in forward mode. We can't evaluate the likelihood formally. We can only simulate events. We can't go back and say what the probability of seeing this particular event is without going back and simulating a billion events and integrating over everything, which is too expensive. So what we do is we simulate a lot of events and use maybe some sort of probability density estimator to be able to make the estimate of this thing. Now, we can't look at things like the 100 million channels. That's too high dimensional space. We can't even look at the 4 vectors, the momenta of the particles either. That's still a too high dimensional space. So what we do is we will derive some small subset of physics-motivated observables and profile the likelihood in those observables. And of course, in doing that, we lose some information. And typically what we do is we'll do that, and then we'll make some cuts. We'll isolate regions in these observables, which means that we'll lose efficiency. And then maybe sometimes use some classifiers to further reduce the dimensionality, but then eventually at the end, we'll profile the likelihood in 1 or 2 ideally uncorrelated observables. Okay? And that's how we evaluate this thing. When we lose a lot of power in these kind of steps, and a lot of things that, for example, Chris does is trying to make the best set of these sort of observables to be able to not lose that power as much as possible. We do better searches. There's an alternative method. I don't want to get into it. I'm going to try to go too long, so I'll skip that one. Okay, so let me tell you a bit now about deep learning. Now, I don't know if I need you guys to explain deep learning too much to you. So my premise is that deep learning is going to help us solve these problems. I just want to quickly say, everybody I think probably knows about neural networks, probably knows about the public inference and this idea that these networks of the right sufficient large size can actually approximate any function to. Now, we have been using neural networks for a long time, as they've been typically shallow networks, and we've done it for a signal background classification task based on sort of high-level features that we get, those variables that we just talked about. That's what we've been doing. I think everybody sort of probably knows the story now that there's this problem for deep networks with the variation gradient problem for when you were doing the stochastic gradient descent of being able to actually get enough gradient on the lower layers to be able to actually train those early layers. These problems have been solved by being a little bit smarter about how you do stuff, and also just having lots of data and then having GPUs so you can actually process that data. And that combination has led to something I'm calling the deep learning renaissance. Suddenly, we knew deep networks would be great. We just couldn't train them, and we didn't have enough computing power to do it. But now we do. So suddenly, all these amazing things can happen because suddenly we can actually use these things. And that's what's going on. So there's these amazing feats like audio, image, and video recognition. You take a picture, it produces a caption for you in text. Text sentiment analysis, language translation. You can train a deep learning-based agent to play video games. You can do these incredible things that have, I'm hoping that you guys have all heard about, okay? But it's really a rich field, okay? So we want to use these techniques and apply them to HEP. And so why? What can we get out of it, okay? Well, we can hopefully get better algorithms. Like these deep learning-based classification regression algorithms generally outperform sort of the handcrafted stuff, okay? So that's good. In some cases, it might actually give you a solution where we don't have a solution. For example, the liquid argon TPC example, we actually are not doing very well. Maybe this will do better without us actually have to engineer anything. And maybe we can do something like unsupervised learning where we don't even have to know the classes or whatever, and this thing can, in data that's sort of ambiguous, can help us understand the structures in our data. So that can give us better algorithms, but we can actually also, it might be easier for us to develop our algorithms. So we'll do something called feature learning instead of feature engineering. That reconstruction that I described to you, it's all feature engineering. We spent $250 million on Atlas over 15 years of physicists and computer engineers working to develop all that software. And perhaps we can do that easier and cheaper if we just had thrown a deep network at it, okay? This is, all right? Right. And I mean, the other thing we can do is sometimes you don't, I need to, maybe if I have to do a study, I have to spend a year developing an algorithm to do it, and then I throw it with an algorithm. Maybe with a deep network, I just throw it at a deep network and that algorithm is built for me. So I can do a lot of our studies much quicker, and that also can help cost. Finally, we could maybe get faster algorithms. After training these things, these algorithms typically run faster than their sophisticated algorithmic approaches that we have. And we can take things like if you have something that's really expensive to calculate, we can maybe encapsulate it in one of these things. For example, this method that I described to you. We can use deep learning generative models to do much faster simulations, for example. And these things are already parallelized, already run on GPUs and HPCs, and there's these new neuromorphic chips that are coming out that are extremely efficient and potentially very, very fast. So but maybe this will sort of help us address those problems we have with high luminance LHC. So maybe the deep learning would be sort of some sort of disruptive enabler of computing for this, because we're right now sort of stuck. Okay. So what I'm saying is that, so here's a typical deep learning thing. Here's a picture. This thing has produced a caption by identifying objects in it and producing some sort of text. Woman in white dress standing with tennis racket, 2 people in green behind her. What I want to do is do that to this, saying, you know, this is such and such particle, and this is the other particle doing this and that effectively. That's the idea, right? That's what we want to do. All right. So I don't know how much everybody is familiar with convolutional nets and feature learning. Let me just quickly just overview it. So the idea here is that before I would go and do feature engineering, I would go and figure out algorithms to give me some features that I can feed into my neural network. Now I just give it the raw data, and it learns the features by itself. And convolutional nets are a good example of something doing that, where if you, for example, doing image recognition, you take an image, you have a patch that can go around. Each patch is going to be a detector of a particular type of feature, you know, a line, a diagonal line, a straight line, or whatever. Every time you see one of those things, you put it into a feature map. You have lots of feature maps. You have lots of these things. You're learning these things at the same time. You do some sort of subsampling, and you do this over and over and over again. And what you see is that if you will see what features, what things activate particular features, the earlier features will be things like edges. If you're doing on faces, later features would be things like eyes and ears and things like that, and higher level features are things like faces, okay? That's the idea, and we want to apply this to it. So the first experiment to actually do this and actually publish a paper was a NOVA experiment. And they're a neutrino experiment. They work on a different technology I don't want to get into too much. But basically, they also get effectively images that sort of look like this of neutrino interactions. And what they did was they actually even looked at what features. So here is a muon-neutrino interaction, the different types of interactions you can see. And some of them, for example, this one has not much, a little bit of hadronic there, and some muonic features. So the thing had learned to identify muons or hadronic behavior, for example. Here's a different type of thing where it doesn't have the hadronic, but has purely the muon features, and so on. So you can even see what it's doing. And the interesting thing here was that they were able to get 40% better electron efficiency for the same background rate. This is huge. So in the meantime, I was been working on liquid argon TPCs. There's a small experiment called Lariat that I've been working on. And we did some work, and we made some preliminary simulation samples, and we did particle identification classification problem. And what I got out of this, and I'm just going to go quickly, is this performance that we see here is better than anything anybody has ever done, and it took me one night to do the whole thing. The microboot experiment actually went off and did this a little bit more carefully, and they actually have a note out doing this, and they also get fairly good performance in doing this. Now, there's a lot of things you can do. You can do particle identification. You can actually identify the neutrino type. You can do things like, if these things are sitting on the surface, we get cosmic rays, and you want to be able to reject those. You can do cosmic rejection. And you can do things, you have to measure the energy, you can actually do the energy regression. This is actually something that I'm personally working on right now. And the interesting other thing is that we found that shallower networks are good enough. Our particle physics events are much simpler than people's faces. Something else that Mackie did was they did semantic segmentation where they got a big detector, they go through the detector, try to be able to find the particles in the detector. So they were able to see that. Here, what they're trying to do is identify neutrinos from cosmics in the detector. So here's a real sort of cosmics, and they're seeing this. They do a good job. These are low probability neutrinos. Sometimes it makes some mistakes, but sort of understandable. And other times it gets the neutrinos. Okay, so they've demonstrated that this works to some level. Now, what's going on now is that I've been working with some of my students. So these studies have been done typically with very small samples. And we wanted to do energy regression, and energy regression ended up requiring big samples. So we've gone through a long campaign of producing a huge amount of data. So we have 1 million events of every one type of these. So there's something like 15 million events that we produced. And we're just starting to do those studies. And some of my collaborators in UCI, for example, trained a network on still a subset of this data for a week until we got significantly better performance than we had other people have gotten, just because we had more data and we can train longer. And we're working on this. This data will be available publicly. If you guys are interested in these things, I can give it to you tomorrow if you like. Okay. Let me tell you a little bit about the next experiment. This is something a little bit different. This actually now sits in the realm of nuclear physics, but here you're looking for neutrino beta decay. I don't want to say too much about it, except that if you discover this, you get a Nobel Prize. And it basically tells you that if you discover this, that neutrinos are their own antiparticle. Okay? And the technology they use is something called also a TPC, but it's a gas TPC, and they actually can get a 3D image out of this thing. And their signal that they're looking for is 2 electrons coming off, and the background is a single electron. And the problem is that these electrons are low energy, and you can't tell the difference between this and that because of multiple scattering. These electrons that travel, they bounce around, and you can't really tell the difference between them very well. The most significant feature that's different is that when the electron actually gets captured at the end or something happens, there's a little blob. So you're looking for 1 blob versus 2 blobs. That's your background. That's your signal. Okay? And so I actually work on this with the guys who did this. We went through and used an out-of-the-box neural network, a convolutional neural network for imaging. And we were able to basically compare it to the sort of standard analysis, get somewhat better performance just doing this. And actually, what we can do is, they don't still have the reconstruction working, and they're still designing the detector for doing this. Well, how can you design a detector without doing the simulation, all that stuff, what parameters you should have for the detector? This is a technique where I can just take simulated data and throw it at this thing, and it gives me a metric that I can get very quickly of how this change to the detector design affected my final results very quickly without having to sit there and spend years writing the software to be able to do that reconstruction. So that's one thing they're doing. The other thing they're doing is they don't know the relative importance of different effects. So you can go back to the simulation, you can turn on and off of different effects and see how it affects your results. So this is what they did. They go on, turn on and off different effects, and they understand the relative importance of different effects, and then if something that's important and they can actually tackle it, they can go and design their detector to go address that particular problem by a different mixture of gas or something like that. Okay? So there's something that they're doing there. This is what the images look like there. Okay? I want to quickly talk about semi-supervised learning. These are, I don't know if people, again, are familiar with these things. Basically, the idea here is that I want to train a network to reproduce this input. I'll give it an image, and I want to train a network to give the image out. But what I'm going to do is I'm going to sort of choke the network a little bit so that I'm sort of reducing the dimensionality of the information. And there's different applications of these. I don't know if you guys have heard about these, but there's things like denoising autoencoders, where what I can do is I can add noise to the input and then give the original input as an output. And these things will learn to remove the noise from them. This has lots of applications in what we do. You can use sparse autoencoders. So basically, there's some latent code representation of your data here. And you can use that for compression or clustering or similarity testing, those type of things. You can do anomaly detection. You can train this thing on some data set and then give it new data sets and look at the reconstruction error. How well did I get this thing out from the computer? Or look at the sort of cluster in the latent space, and I can find anomalies this way. Again, there's a lot of applications there. And I can do something called transfer learning. Maybe I my simulation is not very good, and so I can't label my data. What I'll do is I'll use one of these things to build the model of my data, and then I'll have some control sample. So I'll train this on some large unlabeled data set, and maybe I can find some small labeled data set, and then to be able to further train this thing to do the task that I want. This is something else that you can do. There's really dozens and dozens of applications that you can think of these things. Now, one demonstration of this was done by the HEP experiment, where it's also similar. They're sort of, I don't want to go too much into the things, but they read out sort of this array of PMTs, and they get images like this, and they have different sort of classes, prompt and delayed, inverse beta decay, muon, or flasher, or other sort of classes. And what they did was they used real data, no simulation. And first, they went and they ran their standard analyses and classified the data, and just to see if they can train a supervised classifier to be able to identify things. And then, so they took the classified the data, and they sort of took it down to a 10-dimensional space, and then they did this clustering algorithm, and they were able to identify the different clusters of data in the supervised learning case. And then they did unsupervised, where they didn't tell this thing anything. All they gave it was a raw data. And so this is an autoencoder that does that. And again, so this is the autoencoder, this is the input, this is the output. This is another input, another output. So sometimes it does well, sometimes it doesn't. But again, it was able to, when you look in the latent space and then do a little bit of clustering that space, you would clearly can see that this thing has recognized that muon events are different than other type of events, for example, which is sort of interesting. Now, where I would like to apply this is, for example, in the Atlas Calorimeter. Again, this is a huge calorimeter. Now, this is effectively the data comes out of this is a big 3-dimensional image. And I can apply the same techniques to these things. And if I can get any improvement here, we'll have a high impact. If I improve the identification and or the energy resolution, we'll make all those peaks, the Higgs peak, all those peaks stand up more. And it has a huge impact for us to be able to do that. And another thing I can do is I can maybe turn this into a generative model. And it ends up this, and I'll talk about it maybe if I have still time. I'll talk about how, this is actually, the simulation of particle showering in the calorimeter is really, really expensive for us. So if I can actually build a generative model to do this much quicker, it saves us a whole lot of CPU. This is what we spend most of our CPU on, actually. Okay? And there's high potential because, in fact, the algorithms that we now use to be able to do these reconstructions don't lose all the information there. And the physicists and other interested people can read through this, all the information that we don't use, that if we do use, we can potentially improve all this kind of stuff. Now, the problem here is that this is private data. And if I want to work on this, I can't collaborate with anybody. So the solution is that we go onto what's called the LCD calorimeter. This is a proposed accelerator that maybe is a competitor to the ILC that may be built, it depends on what happens. And they have a detector that's designed for that, and the detector that they designed for this thing has a highly granular calorimeter in it. And this data, since it's not a real detector, we can take out the code, we can simulate this stuff, and no one cares. No one gives us heartache for it. So that's what I did with some of my collaborators. And so we have a very large data set, and we've just started looking at these data sets. We built some 2D and 3D convolutional nets, and we're comparing the performances for distinguishing, for example, photons from pi-0 decays in there. And there's a whole set of things that are happening there. We are going to produce more data. And again, this is another data set that if you're interested in is available. We're producing more of it. And if you like to work on these problems, we're happy to share it with you. Finally, we talked about the tracking in highly localized LHC. So to do the tracking, what you need to do is first you have to prepare the hits. Then you have to, so these are the hits, these are everywhere here was maybe a real hit. You have to go through and actually find those things somehow, something above a threshold. Then you have to start seeding, sort of looking for patterns, because if you do it globally, you can't. So you look for like triples of hits in a row. And then you start doing the combinatorics of how these things can go. And then once you've done that, you'll do the track fitting, and then you do some cleanup. And it ends up, right now with our collisions, we get something about 30 to 50 collisions per crossing. And our data streams about kilohertz are coming out of Detector. We've done a lot of optimizations, and we can handle it. Ends up for the 200 collisions per crossing and everything else at a highly LHC, the combinatorics for that pattern recognition blow up. In fact, they get so big that it becomes completely intractable for us to be able to do it. So we need a solution. We don't have a solution. We don't know what to do. So what we're doing right now is we're We're trying to produce data samples that we want to provide to the community at large and to be able to help us do that. And so some of the people involved in this, and I'm involved in this also, worked on the Higgs ML challenge that you might know. And what we're trying to produce is now something called the Tracking ML challenge. So we're producing a very large data set of these kind of events and the actual baseline default simulation, reconstruction. And what we've done is one of our collaborators has actually taken the Atlas simulation and tracking code and taken it out of Atlas and provided the package and does it standalone for this purpose. Okay. Again, this data set, this is up and coming, maybe by the end of the year. And if you're interested in this problem also, let me know. Okay. I'm nominally out of time. I can talk for a couple more minutes. I have not too many things left. Okay. So some of the other problems that people are looking at are something called boosted object tagging. So it ends up that, let's say you have a W boson. A W boson can decay to 2 jets. And if it's got kind of that W boson is not going too fast, the 2 jets would be sort of spread apart. But as they go faster and faster and faster, they collimate and they come together and they can't resolve those 2 jets. But you still want to say there was a W boson there. So this is something that actually has, in the past few years, become very important for LHC sort of analyses. And to be able to do that cleanly, so what you want to try to do is, for example, here is a typical quark or gluon jet, might look like this. A WZ jet may look like 2 things, and a top jet actually may look like 3 things on top of each other. And you want to be able to identify these things. And we have standard techniques for building high-level features and classifiers based on those to be able to identify these things. We have techniques for doing this. What's sort of interesting, and there's a lot of groups. There's a lot of groups that actually are working on this. And unfortunately, I can't show you this stuff because everybody's working inside the collaborations, and none of that stuff is public information. But there is a group that has actually worked on something very similar and applied it to this problem at Slack, and they did it with their own data, but not really at the calorimeter level, but good enough to see something. They produced something based on sort of imaging techniques called jet images to be able to analyze jets in general. And then based on those images, they applied some sort of a convolutional neural net classifier on top of it. And the reason I'm telling you about this is that what happened there was that as they started looking at the features that this thing was picking up, they started learning new things to actually use in their standard analysis. They found they were able to understand, oh, there's this new observable, there's this new feature. And then they were able to then construct a variable that correlates with that feature, and then now use it in the standard analysis. So even though this was not applied to our data or whatever, by just going through the exercise and looking at what a deep neural network was doing, they were able to learn something to apply to the real data. And I think this is one of the points I'm trying to make. This is a powerful tool for being able to do that kind of stuff. Okay. All right. Generative models, I don't know, again, if people know about this, but as I said, we have this problem with these likelihood approximation sort of techniques because we rely on these forward-going simulations. This is the most computationally expensive thing that we do. And it would be really great if we can actually speed this up. And it would be really great, actually, if we can do simulations based on data. In fact, we don't actually we take our data and train something, and then we can produce more data more like that. Those would be great tools. Think about, for example, that hadronization step, which is physics that we don't know how to do the computation. If I can actually encapsulate that physics into a deep neural net model, that would be very, very powerful. And I can train it on data and then be able to do better, basically, in that modeling. Now, there's different techniques to be able to do this. Basically, starting just from examples, I don't want to go too much into it, but basically there's something called generative adversarial networks, where basically you train one network to produce the data and another network that tries to tell the difference between the data you produce and the real data. If you train them at both times simultaneously, that one network learns to be able to train the data, to reproduce the data. There's something else called the variational autoencoders. Basically, it's the same thing as an autoencoder, except that latent space, what you do is you have a sort of a latent variable, probabilistic model of that latent space, which then, once you build that, then you can go through and you can then just pick a point in that model space and then run the decoder, and then you get an event made. And people use these things to generate random pictures of people's faces and rooms and stuff like that that don't exist but look completely real by just generating. So people are looking at this. This is one of the hot topics, and so one of my friend Kyle and them are actually working on this now with an Atlas. Okay. And in fact, this LCD data set that I provided, if you guys are interested in this problem, is ideal for this. Okay? So let me just finish by talking about something that actually Chris and Paul Jackson and I did on Friday. I got here Thursday night, so I only had Friday, and we worked a little bit over the weekend to work on this. I'm not sure if you're aware, but Chris is actually a pretty amazing guy. When he was a grad student at CMS, he invented this set of observables, or known as a razor, which are really good at separating supersymmetry events from the background events. This is the reference to the paper. And he was in CMS, and I was in Atlas, and a friend of mine pointed it out to me, and I was the one that brought this measurement to Atlas and we did the first measurement of this. And once Chris came here, he moved on to Atlas, and then he has joined our effort, which has been great for us. But Chris and I never had really a chance to work directly together. It was mostly through my postdocs and students, and this was a great opportunity actually to sit down together, because we tend to be on the same wavelength in a lot of things. And we've actually done 3 measurements, and the 4th measurement just happened a few weeks ago. Was presented at their big HEP conference called HEP. And these guys need a well-deserved break because of all of that work. But it was based on something new called a recursive jigsaw, which is an uncorrelated base of observables based on doing successive boosts to get into the frames of the different decay particles. So this is maybe some decay topology from one of his papers. So I just pulled this from the most recent paper. So here there's 2 of the variables, and here's what the backgrounds look like, and here different 2 signal scenarios look like in 2 of the variables. So they're very discriminating and very powerful, and we've been using those. So what we wanted to do was do something simple. We only had Friday. So what his technique does is that you sort of give it a hypothesis of what actually the decay is, and it computes a set of observables based on the hypothesis. And we wanted to see if we can actually distinguish between those different hypotheses. Okay, so we sort of constructed, or he kind of constructed sort of this scenario where you have 2 parent particles produced, and those 2 parent particles will decay, and through that decay, they will go through some daughter particle. And the final state that you will have will be 2 leptons, 2 B quarks, and some missing energy because some particle is missing. And what we want to do is to be able to say and there's 2 ways that this thing can happen, these sort of decay. You can get a B quark from the primary decay, or you can get a lepton from primary decay, and the other particle ends up the other place. And we want to see if we can separate between those. He made a sample. I threw a deep neural network between it. And we were trying to really see, first of all, can we do this? Okay, can we separate between these different scenarios? And then, if we can do that, is there additional information that we didn't use? So here's just a basic example. And this may be bugged because we realized maybe something that we made a mistake on. But so this is sort of the different categories and sort of the ROC curve of being able to identify them. So we did fairly well doing that. And I did that, then we just did it with the 4 vectors, not the features. And we got a little bit better. And it looks like there may be some room for improvement, but this may be, we have to go back and figure out exactly what we did wrong. But that's what we're working on, this type of things. And actually what we're doing now with Paul is we're laying down sort of putting the data samples together and moving the data around, all that stuff, to do a much bigger, nicer study of similar type. Okay, that's what we're doing. All right, so I'm finally done and only 7 minutes late. So for decades, HEP really was the big data science. We produced more data than anybody had. We produced more data in weeks than humanity had produced ever. But then we got overtaken in the mid-2000s by Google and everybody else. And as our accelerators have turned up their luminosities, we're going to, I think, once again, start dominating. So I think in the next decade, we may have, again, more data than anybody else will ever have. The problem that we have is that to process data is just prohibitively expensive. And we need some clever techniques for doing this. And I think that deep learning and neuromorphic processors are a promising solution there. We're really in the early days of investigating them. Deep learning allows us to develop better and or faster algorithms that are generally easier, I mean even cheaper, less manpower hours, to develop and directly apply to data. I showed several examples of that today. Deep learning also serves as a tool to optimize designs and traditional techniques, allowing us to indirectly improve our measurements. I don't have to apply the deep technique to my data. I can use it to understand what I should do. Okay, and I showed a few examples of that. There's a variety of interesting applications. There's still more that I didn't tell you guys about, and many of these have potential very big impact. We are right now producing terabyte-sized public data sets that we will, for the sole purpose of sharing it with data scientists so that we can collaborate with them and to write papers. And there's lots of opportunities for collaborations. And so please, if you're interested, contact me and we can see where it goes. Thank you.
So if anyone would like to leave, you are definitely excused. But if you will take any questions, anyone has any, we can do that.
A quick question. In the very beginning, you mentioned the necessity to having this trigger process to pick up the event. It was not clear later the likelihood function you actually model that process. That's fundamentally alters the process.
You see any better. Even the limiting things you are not interested in. It's not clear to me how do you take that into account later in your analysis?
I mean, it is something that you have to do carefully. First of all, we can simulate everything, and we can simulate a true process.
So you actually do that in a simulation process?
We do that, but then we don't actually trust that. There are standard candles that we use to be able to assess the performance trigger. We actually are taking data also, so we can see the rates of the triggers and measure two things. There are various ways for us to actually validate this and make sure we understand it convincingly. It is a tricky thing at times.
Have you thought about actually putting the nets directly into the detectors? You're saying you have this problem of like how much data do you extract? You could imagine having like
Hopefully one
GAN
day.
basically.
Yes, hopefully one day.
Okay.
I mean, this is where we go. I mean, we're in the early days, but we have a show to work from a lot of stuff, and maybe one day we will do that. I mean, that's my dream, that we have sort of neuromorphic processors that are looking at data live and making decisions.
Or just like extract all that layer, right? And then you just have like
That's-
super compressed.
Yeah, I mean, absolutely, and that would be really cool, but we have a whole community of physicists. We're very, very meticulous about how we do things. So we'll, probably if we want to do that, we'll have to do it both ways the first time. I run a whole experiment and make every old guy and make sure that they're happy with it before we go on and do it next time. Yes.
Have you ever tried the RNN? Have you ever tried other neural networks such as RNN?
Yes, and other people have, and I have also for different contexts. I just didn't show it. So some of the boosted object track stuff, those guys are mostly using RNNs. For anomaly detection, I've been using LSTM autoencoders for time series data, for example. So yes.
Additional questions? In that case, let's thank Amir again.